This presentation will cover the progression phase of internal erosion. After this presentation, you will be able to explain the progression phase of internal erosion, to assess the mechanical and hydraulic conditions for progression, and to assess the rate of pipe enlargement. The presentation will start with an overview of the internal erosion phase, then cover the mechanical and hydraulic conditions prior to getting to how to assess the rate of pipe enlargement. Starting with an overview. Progression is the third phase of internal erosion. For soil contact erosion, erosion of the finer soil into the coarser soil continues and may lead to the development of a pipe in the adjacent soil. For concentrated leak erosion, erosion in a crack or concentrated leak leads to the development of a pipe. For backward erosion piping, the erosion process extends upstream from the point of initiation, and a network of small erosion channels form beneath a roof for the erosion pipes. If the small erosion channels reach the reservoir or river, then a pipe forms. For suffusion, some of the finer fraction is eroded, leaving the coarse matrix of the soil. No pipe is formed, but the permeability of the soil may be increased significantly. For internal migration, progressive roof collapse creates a void that enlarges and moves upward in the embankment until a sinkhole is formed, resulting in stoping. A stope can also be the product of other internal erosion processes. Once initiated and not arrested by filter action, internal erosion will progress under a mechanical and hydraulic condition. For the mechanical condition, the crack must be sustained by hydraulic pressure, and the roof or sidewalls of a crack or pipe must not collapse or swell closed. A stable roof is inherently not applicable to internal migration and stoping, but the pathway must not clog. For the hydraulic condition, sufficient gradient or velocity must exist to provide sufficient energy or drag force to continue to transport particles along openings and off external surfaces in a continuous process. For concentrated leak erosion, absent crack filling or clogging and flow limitation, or lowering of the water level to reduce the hydraulic gradient, erosion will progress because hydraulic shear stresses in the pipe increase as the pipe enlarges. Thus, the likelihood of progression for concentrated leak erosion through the embankment usually considers three nodes: holding a roof, upstream flow limitation, and crack filling action. Two are related to the mechanical condition, and one is related to the hydraulic condition. All three nodes appear in some generic internal erosion event trees, but they are usually worded to only apply to concentrated leak erosion in zoned embankments. There are some common mistakes associated with other internal erosion processes when such event trees are used. For example, a stable roof for node 4 is not applicable for internal migration because stoping involves the progressive roof collapse regardless of material type. Therefore, this node should be eliminated or modified to must not clog by adjacent materials. Node 5, flow limitation, and Node 6, crack filling. Neither are applicable for backward erosion piping or concentrated leak erosion through a homogeneous embankment. The mechanical condition for progression. Progression can stop if a crack is not sustained by hydraulic pressure, if the roof or sidewalls of a crack or pipe collapse, or if the sides of a pipe or crack swell, either closing the crack or reducing the opening size, which reduces the hydraulic shear stresses on the surface of the pipe or crack. Progression can also stop if particles from an upstream zone of the core are transported into the developing pipe and eventually seal the filter, which is known as crack stopping. For holding a roof, two primary factors are the presence of a continuous harder soil layer or embedded structure, and the fines content being greater than or equal to 15%, regardless of the plasticity of the fines. Non-plastic silts, sands, and gravels will generally not hold a roof since the roof collapses upon saturation. Partially saturated and high fines content non-plastic soils may hold a roof near the phreatic surface, but the roof is sustained by pore pressure suction and may collapse upon saturation. As for secondary factors, moist soils are more likely to collapse upon saturation than saturated soils. Loose soils are less likely to hold a roof than dense soils. And cyclic reservoir levels are more likely to cause roof collapse than steady reservoir levels. In most cases, the core of the embankment is capable of providing a roof to a developing pipe in the foundation, because it is typically constructed of impervious soils or semi-impervious soils with sufficient fines. In the upper figure, a homogeneous embankment provides a roof to a developing pipe in the foundation. However, if there are upstream or downstream zones of non-plastic granular material in the embankment that are not capable of supporting a roof, for example rockfill or gravel shells, then a pipe through the foundation may not be able to fully develop, as shown in the lower figure. Examples of roofing are shown in these photographs. On the left, the exit hole of a soil pipe is shown. The top middle photograph shows a test pit excavated to investigate a boil, showing the vertical pipe through the top stratum. The bottom middle photograph shows how alluvial material below basalt bedrock in forebay's foundation piped, which connected to the forebay through lava flow tubes, penetrated the forebay blanket, and created a sinkhole. The sudden high uplift pressures on the base of the basalt provided uplift below the embankment. Collapse and fracturing of the basalt foundation led to increased flow and eventually breach of SWIFT number 2. On the right, hard pan layers shown in the overhang formed the roof at A.V. Watkins Dam. Fine sand was piped and deposited in the south drain. With the middle breach of Missouri River Levee Unit L575, located west of Hamburg, Iowa, and just south of the Missouri-Iowa border, multiple pipes progressed towards the river, but it was the fourth one that ultimately led to breach. The first incident occurred on June 4, 2011. The levee sponsor noticed an approximately 10 to 15 foot wide slump of the levee crest. A contractor was called on site to repair. A second slump occurred on June 5th, about 100 feet south of the first slump. It did not develop into a full breach since the levee collapsed in on itself and shut off flow. The third partial breach occurred on June 9th, about 80 feet upstream of the first partial breach, and was quickly repaired. Locals measured a large scour hole along the riverside toe of the levee that was about 20 to 30 feet deep. The fourth slump occurred on June 13th, and a 10 to 15 foot wide full breach occurred in the vicinity of the partial breaches. Within an hour, the breach widened to 150 feet. As previously mentioned, the presence of a structure or hard layer and soil properties are primary factors to consider in roof formation. This table summarizes the likelihood of holding a roof for various materials. As shown, soils with a fines content greater than 15% are much more likely to support a roof than soils with a fines content less than 15%. The probability should not be used directly in a risk assessment, but rather used to help develop a list of more and less likely factors during a team elicitation of probability estimates. Progression may stop if particles from a zone upstream of the zone are transported into the crack or developing pipe and eventually seal the filter. One of the purposes of transition zones is to provide a source of feed material into a crack in the core to prevent piping. For crack stopping to occur, there must be a filter or transition downstream of the core to trap the eroded particles, provided the leakage flow is not too great to break out or move around the healed zone. Therefore, this note is generally limited to concentrated leak erosion in zoned embankments. Here is some suggested guidance for likelihood of no crack filling action based on the characteristics of the embankment zoning. There is no crack filling action for homogeneous embankments or embankments with no upstream zone. Therefore, the probability is 1. If an upstream granular zone and downstream filter, transition, or other granular material is present, crack filling action is dependent on the compatibility of the particle sizes of the granular soils upstream of the core and in the downstream filter transition. Crack filling is more likely to stop pipe enlargement when the core is deficient in sand-sized particles, and these particles can be washed in from the upstream zone. This aids in sealing of the downstream filter zone. If the core is well graded and has sand sizes present, the potential benefits of crack filling are less because the sand-sized particles are already present. The probability should not be used directly in a risk assessment, but rather used to help develop a list of more and less likely factors during a team elicitation of probability estimates. The crack filling erosion test focused on evaluating the ability of crack filling action by particles eroded from granular materials located upstream of the core. It includes the downstream filter necessary for crack filling action. Upstream material was not drilled and had little to no fines in order to supply fines to the cracker pipe in the core and not itself sustain an open cracker pipe. Crack filling action is a rapid mechanism, controlled mainly by parameters influencing the formation of a self-filtering mechanism. So it's a particle retention problem as discussed for the continuation phase of erosion. Foster and Fell erosion boundaries can be used to assess if the particles detached from the erosion pipe in the upstream zone and core can seal the filter at the downstream zone. For the tested gap-graded soils, crack filling action is governed mostly by two factors. One, the sand content that can be transported into the crack, the higher the better, and fines content and plasticity, the lower the better. And two, the relationship between the fine sand content of the upstream material and the D15 of the downstream material. The higher the fine sand content and the lower the D15, the higher the likelihood of crack filling to occur. Broadly graded soils that can sustain a crack or pipe are very unlikely to be able to provide crack filling action. Nevertheless, they can avoid the enlargement of the pipe and even diminish the leakage flow, providing the particles to the downstream zone that are required for a filtering mechanism. A hydraulic condition for progression. For the hydraulic condition for progression, water seeping through the dam, levee, or its foundation must be doing so with sufficient velocity to provide sufficient energy or drag force to continue to transport detached particles along openings and off the external surfaces of the embankment in a continuous process. Thus, there must be sufficient flow to continuously transport detached particles to an exit. For concentrated leak erosion, as the pipe or crack enlarges, hydraulic shear stresses increase. Therefore, erosion will progress unless the hydraulic conditions change to reduce the hydraulic shear stress causing the erosion. In small reservoirs, the water level can drop below the level of the pipe to reduce the hydraulic gradient and hydraulic shear stress. Another scenario is flow limitation, when flow in the concentrated leak is limited by head loss in the upstream or downstream zones, causing the pipe to reach an equilibrium condition. This typically occurs in an upstream zone, for example, a concrete face slab, that can limit flows into the crack or pipe to sufficiently reduce hydraulic shear stress below critical levels to arrest the erosion process. For backward erosion piping, there is a critical gradient above which the particle is detached. This is an exit gradient consideration. And there is also a critical flow velocity above which the soil particles will be transported in the pipe. This is an average or global gradient consideration. Backward erosion piping is the only internal erosion process where the hydraulic condition for progression is evaluated. Three methods were discussed during this training. Progression of the pipe stops if the average gradient is lower than the critical gradient. The hydraulic condition for progression of soil contact erosion is similar to concentrated leak erosion, but erosion may not progress if finer soil clogs the coarser soil. For suffusion, given the eroded soil is carried away, the hydraulic condition will become increasingly able to erode the finer fraction as the permeability increases. For internal migration, given a vertical downward gradient, erosion will continue to progress unless clogging occurs. Factors to consider when assessing upstream flow limitation are shown on the slide. Concrete or sheet pile walls within the embankment or that fully penetrate the foundation soils greatly increase the likelihood of the flows being limited. Modern concrete barrier walls, crossing the internal erosion pathway, typically extending into rock, that are in good condition, have the best chance for success. Steel sheet pile walls may be less effective under poor driving conditions or poor construction techniques. Concrete or steel membranes, soil cement slope protection, geomembranes, or other linings on the upstream face of the dam can be effective, depending on the condition, but potential erosion of the underlying support for the facing may be an issue. Flow through open defects can be limited by aperture size. However, flow velocities could be quite high. This could lead to stoping or internal migration. Upstream fine-grained blankets beneath and around the dam may not prevent initiation of erosion, but may be effective in limiting progression. Flow limitation may occur due to an increase in head loss across an upstream blanket. This slide provides some guidance for concrete elements in the embankment and cutoff walls in the foundation. The flow limitation erosion test focused on isolating the influence of flow restriction action due to the presence of materials located upstream of the core. No downstream filter was included to isolate the upstream flow limitation. The core and upstream material were drilled to simulate common cause defects, the worst case since flow will not be restricted. Upstream flow restriction action and crack filling action may occur simultaneously. Flow restriction action is governed by grading, plasticity, and compaction characteristics of the upstream soil. In gap-graded soils with 5% fines, hydraulic loading and type of fines are critical. For the tested coarse, broadly graded upstream materials, the effectiveness is strongly dependent on the soil gradation, the fines and gravel contents, plasticity of the fines, and compaction water content. For tested upstream materials, soils with plastic fines appear to be associated with higher likelihoods of being effective in restricting the flow than soils with non-plastic fines. The finer the soil, the higher the likelihood of restricting the flow. This trend may not occur on upstream soils considerably coarser than those tested, in particular in soils with high hydraulic conductivity and that are unable to sustain an open pipe. Some tests have shown that soils compacted fairly to the dry side are likely to restrict flow, mainly due to their self-healing abilities. However, it should be noted that this observation might not be valid in soils with highly plastic fines. For the tested gap-graded upstream materials, hydraulic loading is critical. For soils with 5% fines, the plasticity of the fines is also relevant. For similar gradation and loading condition, soils with plastic fines are more likely to restrict flow than soils with non-plastic fines. In addition, it appears that internal stability and hydraulic conductivity dictate whether there is flow restriction or progression of erosion. Finally, the higher the resistance of the core material, the higher the likelihood of the upstream material being capable to limit the maximum flow rate. The following table from the Best Practices Manual can be used to help assess the likelihood of progression of internal erosion. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address a continuous stable roof and sidewalls. The factors in this portion of the table address upstream flow limitation. And the factors in this portion of the table address self-healing by an upstream zone. Assessing the rate of pipe enlargement. The relationship between erodibility parameters and initiation and progression of concentrated leak erosion was previously provided. This excess shear stress equation can be used to assess the rate of pipe enlargement. The time for erosion to progress is an important factor for assessing the likelihood of successful intervention and is dependent on the soil erosion properties. Breach mechanisms vary in their time to fully develop. Therefore, the likelihood of successful intervention should also consider the potential time available based on the breach mechanism being considered. This is discussed in more detail in the intervention presentation. The duration of the critical loading is also an important consideration and can complicate the assessment of the rate of enlargement significantly. Rate of pipe enlargement in the progression phase is characterized by the erodibility coefficient. Based on whole erosion results, this figure shows the approximate time for a pipe to enlarge from 25 millimeters to 1 meter in diameter as a function of erosion resistance and hydraulic gradient based on the assumptions shown. Erosion resistance increases from left to right. The approximate time to erode to 2 meters is about 20% greater. Even in the most resistant of soils, enlargement occurs in only 100 to 500 hours, somewhere between 4 days to 3 weeks. Toolbox overview. There is no toolbox specifically for the progression phase. Please consult the Best Practices Manual in this presentation for guidance on assessing the mechanical condition for progression. Assess crack filling action using the RMC filter evaluation continuation toolbox, where an upstream zone and eroded core materials are base material and the downstream zone is the filter material. Assessing the likelihood of upstream flow limitation is very subjective. If the upstream zone is effective at flow limitation, adjust the hydraulic gradient across the core when assessing initiation using the RMC concentrated leak erosion initiation toolbox. Assess the hydraulic condition for progression of backward erosion piping using the RMC backward erosion piping progression toolbox. Assess the rate of pipe enlargement using the gross enlargement worksheet in the RMC breach toolbox because the pipe enlarges to a specified pipe diameter at failure. The primary references used to develop this presentation are listed on the slide. This concludes the presentation on progression.